front of people, and then things just don't go very well. Hate that. It's the worst. It's like the nightmare that you have as a professor is that like you're up there and like you know what you want to say, but you just can't say it. Yeah. So I lived that this morning. I'm not going to upload that video. Well, I mean, assuming this one goes better, it's no guarantee. So, let's give this a shot. So remember how we did the first couple sections of this last time. We started talking about DC motor performance, and we said, okay, hey, so we've got our pretty good motor model here that has a voltage source. The windings have a resistance and an inductance. Goes through an ideal transformer. We have some damping internal to the motor on the mechanical side, Bm for the bearings inside the motor, and then the rotor inertia, Jm. And then we load this motor with a brake, essentially, a torque source that we can control, a brake we can control the torque for. And this is our test setup to characterize the motor. The key motor curve is the relationship between the speed of this output and the torque of the brake. Okay, that relationship is sort of the key relationship that we're trying to derive. But we're also going to look at some of the other commonly used curves to characterize a motor. So, the voltage source is typically just set to full throttle for this. At 60 volts in our case for this motor. 60 volts is the max voltage. So you put 60 volts in and you have no brake. And then you measure what the speed is. Then you add a little bit of brake in. Measure the speed. It's going to slow it down, right? The brake's going to slow it down. So then you add a little bit more brake, a little more torque source. It's going to slow it down a little more. Measure that. So you wait till steady state before you take all your measurements. So you do it again, wait till steady state. And you just keep applying more and more brake until eventually it's going to stop the shaft, right? So even though you have full bore voltage applied, you've applied so much brake that you've stopped the shaft. And then you have this so-called stall condition where your torque of the brake is at its maximum. You're maxing out the torque of the brake before it. I mean, you can keep trying to add more and more torque with this brake, but it's not going to work. Brakes don't really work that way. You keep pressing it harder and harder, but it's not going to add more torque to the shaft. Once it's stopped the shaft, it's stopped. So brakes can't turn things backwards the other way. Just brakes, you know. You just can't do that. They're pretty lame. So that's what sort of the curve's going to look like. It's going to start off at max speed, and then you're going to apply brake, and the speed's going to drop all the way down to 0. And then that's our max torque. So that's the motor curve that we're going to derive. And the other motor curves are going to be related to that as well. So we went through and we did the modeling aspect, which we discovered that the input vector now, instead of having just a voltage source, we also have the brake's torque source, right? The only equation that changed from the model that we did in the previous lecture, the only equation that changed was this continuity equation, which corresponded to the contour that we drew around this node. Because in the model that we had done previously, we didn't have a torque source on it, so we included that, which leaves us with this state model. And I just hate how these brackets don't come in, but what do you do? On the PDF on the internet that hopefully you have in front of you, printed out, these should look nice. So these are our A, B, C, and D matrices for our state equation and our output equation. So now we're going to embark on an analysis of the steady state performance. We're going to use MATLAB to do it. We didn't have to sort of expose the MATLAB. I needed to plot this stuff, so I needed MATLAB to plot it. But I figured I might as well let you guys see how I do it. The M file associated with this MATLAB script is available on the internet under the so on the dynamic systems page. There's this little source code link at the top, and it's got a list of M files that we use. So this is one of them. So you can download it. There are a few cells that I hid from the PDF because like initialization, like clear and stuff like that. So they're in their M file. So if you're on the M file, it'll be fine. Okay. So first off, we're going to define some system parameters. So I'm going to put in the KT and KV from the spec sheet. Also the max torque and the max angular velocity, which are given in the spec sheet for the motor. We're actually going to find that the numbers that we're going to get are close to this, but they're not exactly these. And we're going to have a little discussion at the end about why that might be the case. Oh, I didn't plug in the good mic, so I guess we have crappy sound for this video. That's okay. It's better than crappy instruction. So the spec sheet values are going to be a little bit different than the values that we're going to talk about in terms of these max values. And it mostly comes down to just a little bit sensitivity to differences in parameters here. Then I just define like how do you convert Newton to an ounce force, and how do you convert a meter into an inch. I convert the KT spec value into SI units, and then I also define a conversion for radians per second to from kilo RPM, and that gives us KV in the SI. And I didn't print them out here, but you can check that they're very, very close, although there's some round-off issue that arises here because of the way they're presented in the spec sheet. There's 3 significant digits, and so when you do this conversion, the numbers don't come out identical, but they're close. So, great. So Jm and Bm are the motor inertia and the motor damping coefficient, both given in the spec sheets as well, although I put them in here in SI units. I just took the SI unit version. R in ohms, L in henries, and then I say, oh, TF is we're just assigning KV SI. Could have done KT SI, same, right? They're the same value essentially. They're supposed to be the same. They're very close. So let's investigate what happens in steady state. So in steady state, which we're going to call x bar. So x is our state vector, and we're going to, if we put the bar over it, we're going to say that's the steady state vector. I know when we draw it like this, it has the arrow, so it would be like that, bar. It's kind of weird looking, but so the system is in steady state when x dot equals 0. So when nothing's changing, it's in steady state. The state equation then becomes 0. So x dot is on the left-hand side, so we say that's 0, is equal to a x bar b u bar, where u bar is a steady input. We have to have a steady input if we're going to have a steady output. You can't have an input change. I mean, well, I shouldn't say that. If the input has no effect on the state, that doesn't have to be true. However, in every case that's interesting, the input has an effect on the state. Otherwise, it's not much of an input, is it? It's like if you chose the input to your motor system to be, I don't know, a merry-go-round's rotation over there, it doesn't affect the motor at all. So the merry-go-round might be going round and round, and your motor isn't changing at all. So I don't know. Merry-go-round was on my mind. Just want to go to the fair. Actually, beyond the merry-go-round, like all the rides would make me puke. So not into that. Roller coasters I like, but the ones that spin, I can't do the spin stuff. I don't know why people find that fun. Why is it fun to spin around and get dizzy and nauseous? That's not fun. The roller coaster thing is freaky, and then it makes your stomach go, but that's fun. I actually like that. To a point. The loop kind of freaks me out. Where you go upside down like that. I'm not a huge fan of that. I do like the one where you go way up though, and then you go whoosh down, and you're like, shh. That's fun. I do enjoy that. That part of the roller coaster is fun. I also don't want to think about like what if one of these things broke and I went careening off the side. That'd be a bad way to go. Well, actually, not that bad compared to other ways. Going is just not fun. I just think that's the worst part, having to die. Okay, so if you solve this,
Happy Friday.
yes. Did I mention that I didn't get a lot of sleep? This is going so much better than this morning's lecture. So, if we solve for x in this expression, then we get. So using a little linear algebra, but not super complex linear algebra, we subtract over the bu term, and then we take a inverse, left multiply both sides, and we get this solution. And so if we have some constant input, then this should be our steady state value. So we could go through and do a whole simulation of this, but you can actually find it analytically pretty easily, so that's why we just did it this way. And so let's compute our steady state solution for a constant voltage input Vs equals V bar and braking torque Ts equals T bar. Now we have the ability to use some symbolics in MATLAB, the symbolic toolbox, which it goes against everything I believe in to use the symbolic toolbox in MATLAB. I really don't like it. However, for this case it was pretty easy, so I just decided to do it. So you declare the variables to be symbolic variables. I use these underscores just to differentiate between the variables that I use for numeric values and the symbolic values. So A matrix, B matrix, the input vector, and then I just go through and just compute this expression, 4.6, which is very easy to do. I do this little tricky stuff with this denominator factor, just because if you notice in the output, so this term shows up in every, or this factor shows up in every term. So you can divide that out of the matrix. So it's kind of nice to do that. So a little more human readably, let's write it out. We have that, so omega j and IL were the two state variables, but we are characterizing the motor, and so we like to think about it in terms of omega 2, which is the same as omega j, but one side of the second side of the motor, 2 side of the motor, and 1 being the inside, so current 1, which is equal to IL. So it really doesn't matter, omega j and IL, or omega 2 and I1. So we rewrite them omega 2 and I1, and then we say, okay, what is that equal to in the steady state? So omega 2 is equal to this, which is just a constant, right? Constant. Times TF Vs. Vs we're going to just set for the motor current to be full bore, 60 volts, right? So that's actually just a constant. and minus R times TS. So TS we're going to vary. We're going to vary the braking torque. And that's the one thing that we're changing on this side of the equation. So as we change the braking torque, the speed is going to change. So this is exactly the motor curve we're looking for, right? Great. So 4.7, motor curve. We're going to plot a few motor curves together in a second. So, but we're gonna use 4.7 as one of them. The next one is I1. So once again, constant, same constant. Constant, yes. And then we have the torque changing. So not only does the speed change with the braking torque, the current changes with the braking torque. Okay. So these are two of our motor curves. These are the two, I would say, most important motor curves. The next two that we're going to derive are important too, but they're a little more subtle, so we have to introduce them for a little bit before we do the plots. So let's focus. So I discussed that. Okay, other common curves, the current I1, then mechanical braking power, P brake, which is the torque source, the brake torque source, multiplied by however fast it's going. So mechanical power is torque times the angular velocity. So that's what we do for the brake. Now, the reason we care about the brake power is that's essentially the output power, right? So the motor is doing work for us, and the power that it's delivering is being dissipated by the brake. I mean, this is a test setup where, I mean, we're generating heat with the motor, which is really not a good thing to do with a motor. But that's we're trying to characterize the motor, so that's our setup. So actually, the output power is the brake power, however much power the brake is dissipating, right? Which is weird. I mean, it's not typical that braking power, like the power dissipated by a brake is like the power you're delivering. Usually that's like waste power, right? But in this case, since we have this test set up, we're delivering power to the brake because that's the way we like to characterize the motor. If it could be some other power that we're delivering, like this could be some system that is doing some work for us. For instance, maybe the motor is driving a fan or something like that, and that fan is providing that load torque for us. But from now it's a brake, but typically it's not a brake, right? Just like keep that in mind, is like we don't always put a brake on the output of our motor. In fact, I would say only if you're like have a vehicle that you want to stop would you put a brake out on that, but or some other rotation you wanted to stop. So typically you don't put a brake on, but for this, we're characterizing the power output as being the brake output power. And then there's going to be an efficiency, right? Because we deliver, so power goes into the motor from the voltage source. That's where we're like, that's the source power coming in. Like the motor is taking in this electrical power and it's giving us mechanical power that we're dissipating in the brake, right? Now, that power that's delivered, so the power that goes out of the voltage source and is delivered to the load, the brake, there's an efficiency associated with that because the power output doesn't all, the power input doesn't make it all to the power output, okay? You don't have perfect conversion here because we didn't assume we have a perfect transformer model. We assumed that there is this resistance in the windings, right? We assume there's resistance in the windings, and we assumed that there's damping in the bearings of the motor. So there's some power that's being dissipated internal to the motor, right? That's why the motor heats up. The motor's going to heat up because we're dissipating some power. So the resistor here converts electrical power into heat, right? Flow current through a resistor, power dissipated by the resistor is the voltage across the resistor times the current through the resistor. And if we wanted to write that in terms of the current flowing through, V equals IR. So we have IR squared times R, right? So if you flow more current, you're going to dissipate more power through this resistor, okay? The output side of this, so the mechanical side, also dissipates power because the rotor has a bearing associated with it, and the bearing is going to have a damping associated with it, and it's going to generate some heat as well. So we have the power dissipated by the bearing is equal to, it's always the cross variable times the through variable, BMT, BM. And if we were to write this, the torque is equal to B times omega M, so we have B omega M squared. So the power dissipated by the bearing is proportional to the square of the speed, right? So high current, high resistor dissipation of power, high speed, high bearing damping dissipation of power, okay? And since we have this idea that we know in our motor that the current is proportional to the torque, right? And the output power here, we said that the torque and the speed are essentially going to be trade-offs on our motor curve, right? Torque and speed. So at one end of this curve, we're going to have a dominating rotational speed, so damping power dissipation. On the other end, we're going to have a dominating resistive dissipation of power. So there's going to be this sort of trade-off, and there's going to be a peak efficiency somewhere where there's the trade-off is sort of optimal for us. So that's another one of the curves. We're going to see at what operating point are we delivering power most efficiently. So we'll look at that curve extensively. So there are those are our values that we're going to be, let's see, right here, that we're going to be plotting. And this next little bit is just me writing the braking power and the efficiency in terms of the variables that we know. And then we just do the in MATLAB, we can just evaluate this function. So the efficiency equation is 4.11. The power dissipated by the brake is 4.10. The current is 4.8, and the speed is 4.7. So we have here let's see, this is 4.7, this is 4.8, this is 4.10, and this is 4.11. Okay, so those are our four motor curves. And essentially in MATLAB, all I'm doing is I'm evaluating those expressions at a bunch of different values of torque. So the torque is our independent variable. We're going to say, okay, I apply a braking torque of 1 Newton meter. Apply braking torque of 1.1 Newton meter, etc. And I'm going to compute what all of these values are for those torques, those braking torques. Now, I did do this one thing here. So I said, oh, okay, VS, our voltage, just full throttle, 60 volts, which is the typical way to draw the motor curve. Although technically there is a motor curve for each input voltage, each source voltage. We're going to use the max, which is common. I compute the max torque that we're predicting. And the reason that I'm doing that there is we're going to talk more about the max torque and the max speed in a moment. The reason I do it there is that I want to generate points from 0 torque to the max torque. I don't want to go beyond the max torque because, remember, once the shaft stops, we can't really apply anymore because it's just a resistive element, right? It just resists motion. So once you've stopped, you can't do any more. So that's why we stop it at the max torque. So we generate an array from 0 to the max, and then evaluate what each of these values is going to be for each value of torque. Okay? So then let's plot them. So the plot is on the next page. So freaking beautiful. This is a really nice plot. I've been watching The Office in the background of my life lately, and I feel like Michael Scott is my spirit animal. Okay, so the torque goes, the units of all of this stuff is base SI units. So 0 to 3.6 something Newton meters as being the max. And we're going to compute then these 4 different curves associated with these different braking torques. Now, the first one is our sort of like gold standard for a motor curve, and that is what is the output shaft speed, omega 2, as a function of this braking torque. At full throttle, remember we're doing 60 volts for all of this. So 60 volts, full throttle, and then no brake is down here, right? 0 torque, so no brake. And then up here is full brake. So with no brake, the red curve is the one we're looking at here. This is our max speed, omega max. And then we linearly decrease as we increase the torque of the brake to the max torque at this point. In between, we're essentially trading off between speed and torque. And that's one of the sort of key concepts when you're designing with a motor, is that you're always trading off between speed and torque. So you can either get high torque and low speed, or low speed and high torque, but you can't really have both. Okay? Or there's a trade-off. You can't have max of both. You can max one and min the other, or vice versa. Okay, the second curve is this current. So that's the green one. This is the current in amps. So as you increase this torque, so remember your full voltage the whole time of your input. As you increase the brake torque, your current is going to increase more and more. And that's because your torque draw, essentially, you're drawing more torque from this motor. And when you draw more torque from the motor, that's the same thing on the mechanical side, you're drawing torque. On the electrical side, you're drawing current, right? So as you draw more torque, you're drawing more current. And that's what's happening here. So as we go to full brake here, which means that we're stopped, right? So the speed curve says At full torque, we're stopped, which we call stalling. So the motor is stalled at that point. It's stuck. The brake is fully on. Or if you're thinking about just standing there with like the shaft coming out of the motor, you just grabbed it and you're holding it, you're not letting it move, but you still have the voltage on. Okay? That's stall. That is bad news. Okay? It's okay for a short period of time, but remember, when you've got all this current flowing, you're going to heat up the armature and you're going to damage stuff. So the max continuous current that you can flow through this thing was like 4 amps, I think, from the spec sheet. I don't remember, what was it? I didn't put it on this one. Do you guys remember from last lecture? Anyway, I think it was around 4 amps. So you're like, you can't. So up here, this is like 40 amps almost. Well, 36 amps at this full torque. You can't run that for very long. The question of how long needs a dynamic response model to answer that question. But you do know that you can't just continuously run this. So that's danger zone up there. Okay? Okay. You are, so I could write danger zone. Archer fans? Yeah? Danger zone. Yeah, I love that. Okay, so next we've got so we did our speed, we did our current. Now let's do the power. So the power delivered to the brake, remember, is the torque multiplied by the speed. So the torque multiplied by the speed, if you have max speed but 0 torque, well, that's, if you multiply them together, you still get 0. No matter how big your max speed is, if you multiply it by 0, you're still getting 0. So no power is actually delivered to the load when the brake's not engaged. Okay, when you're not actually supplying any torque to the load. On the other end of the spectrum, when you're down here on speed, so you're slowed it way down to 0 with the brake. You're supplying torque to the brake, but you're not supplying any speed. Therefore, the product of the two is power. There's no power being delivered. In between, there's this trade-off. So you're multiplying the two together, the speed and the torque. So when you have your speed, which is decreasing here, and your torque product maximized, which is halfway to the max, that's when you're delivering the maximum amount of power to the load, the brake in this case. So you have that power curve, so the power that you're delivering, which is really, I mean, when you talk about the motor, you care about that power most, right? You care about how much power you're delivering to the mechanical side. But you also care about how efficiently you're delivering that power, right? So there's a place where you can flow power maximally, which is a torque about there and a speed about there. So the halfway in between is the optimal place to get power transmission. Now, if you care about efficiency, you care about how much power you're delivering from the electrical source and how that compares to how much power you're getting out, right? Because you're delivering power also on a curve, and I kind of wish I had plotted that curve, but I didn't plot that curve. Essentially, you're delivering power that is the product of the current and the voltage of the source, right? Current and the voltage. And that power, if you divide the power you're getting out by the power you're putting in, that's the efficiency, right? So you want to know how effective you are at getting power out of this thing given a power into it. And that depends on the torque too. So when you are down here at low torque, which is high speed, when you're super low torque and super high speed, you're not getting any transmission of power because the power out's zero. So no matter how much power you're putting in, power out's zero, your efficiency is not good. Bad efficiency. So when you're working at the highest speed, the max speed, you actually aren't delivering any power at that point. So not so great. Similarly, on the other end of the spectrum, when you're not getting any power out because you're not moving, there's no speed on the output, you're once again not delivering any power, so your efficiency is going to be zero. Somewhere in between there's going to be a maximum, okay? And determining where that is, it's we have this expression for it right here. So determining where that is, you could determine it analytically by finding the maximum of this function, maximizing that function as a function of Ts. And you guys know how to do that. Take the derivative with respect to it, set it equal to 0, solve for that point, and then evaluate it, the function at that point. So, yeah, so if you take the derivative of this and set it equal to 0 with respect to Ts, you're looking at this being just the slope, omega 2 over I1 Vs is the slope of it. So, oh, well, it doesn't work. I thought I was going to be able to just like flip my way through that without actually thinking it through. We're going to ignore that. I don't remember. I think that the problem is that, oh yeah, we have other things depending on Ts here. So this omega 2 is a function of Ts. You can't just treat it like a constant. That's why that didn't work. We're going to ignore that. That was what this morning was all about. Me just like going off on a tangent, thinking I was going to be okay, and not. So, not going on another tangent. They teach you that when you first come up for professor. They're like, you really shouldn't do anything in class that you didn't prepare before. It never works out. Never do math in front of people that you haven't done before and have it in your notes. And I always don't heed that. And then I usually am fine, but sometimes it doesn't work out. Okay. So, and the worst part is that you still have to die. Okay, so you have this efficiency that has this peak here, and we could analytically explore it, but I'm going to leave that as an aside. We can just compute it just based on the values that we had, just evaluating them and taking the ratio, which is what we did here. And we see that it peaks here at relatively low torque and relatively high speed. So this is the peak. It occurs at a speed of, whatever this is, 590 radians per second, and a torque of like 0.215, something like that. What you're doing here, remember, as you increase high speed, you're getting a lot of damping dissipation. Okay, so super high speed, damping dissipation. Super high current, you're getting a lot of resistive dissipation. So that's where you're losing power to those two things. So you're trading off between resistive dissipation and damping dissipation. And there is an optimal value in here. And notice the efficiency is like, I don't know, what is that, 0.85 or, yeah, it's like 0.7. That's maybe even 0.9. It's close to 0.9. So almost 90% efficient at that point. But efficiency really sucks most of the places. So really, I mean, you're generating a lot of heat with this motor, right? Just like you just can't help it. You just do. Motors are not super efficient. I mean, they're not bad, but that's just what you're left with. That's just all you can do. Okay, so good. So this is our, so this, I mean, that's really all there is about the motor curves overall. But we want to discuss one aspect here in particular, and that is this discussion of the max speed and the max torque. Because the spec sheet, so the spec sheet didn't give any of this stuff. Remember, we actually derived this analytically from our model when we based it on a couple parameters from the spec sheet, though, right? We did not base it on the max speed and the max torque that they gave us in the spec sheet. We based on the resistance, so the resistance of the armature, R. So if you look at these equations, resistance of the armature, R, the damping in the bearings inside the motor, and the kV or kT value. Okay, those are the parameters that we use to determine what the max torque is and the max speed is, and deduce the entire curve. The spec sheet, however, does give a max speed and a max torque. So if you wanted to shortcut this whole process, you could have just said, oh, max speed occurs at 0 torque, so draw that dot on the curve. Max torque, 0 speed, draw that dot on the curve. Straight line in between. That would give you your red motor curve. It doesn't give you the other ones, but it gives you the red one. That is a good way to go for a quick little analysis. Okay? If you want to get in more depth, you got to go with the full model. What's nice about our full model is this is the steady state version of it, but we also, as we'll talk about on Monday, we also have the ability to look at the dynamic response of the motor, okay, which there's not a lot of information on in the spec sheet. So our model is going to give us a lot more information than is given in the spec sheet. But there's a discrepancy between the value of omega max that they give and our omega max. So our omega max, if we compute it, is 614 radians per second. The one given in the spec sheet was 628. The max that we compute for the torque is 3.65, so that's like 3.65, and the max in the spec sheet was 2.82. So if we call the spec sheet the the real or the true value, and we compute the percent error for the prediction that we just came up with, the speed, max speed, is 2% off, which isn't bad, and the torque is almost 30% off, which isn't great. I mean, it's not horrible. 30% in the scheme of things isn't that bad, but it's not great. It seems like we would have a better value. And so the question is our model kind of off, or like what else could be going on here? Do we have maybe our model's not very good? I'm actually gonna, I don't have the time to go into the justification for why this is the case, but motor curves. So you might say, oh well, it's probably not actually very linear. It is actually pretty linear. So these motor curves are actually quite linear. If you go through and you do this test and you apply the brake and you measure the speed, you're going to get values that are pretty close to this curve. Okay, but what I think is going on, so really their curve is more like it goes more like this, right? So their max torque is 2.8, so somewhere in there. So this is T max spec. And the reason that there's this gap here, it's this 30% error, if you will, I suggest is almost certainly due to a couple factors that both are related to the max torque expression, which we actually have down here, max torque expression is TF over R times VS, right? So T max is equal to TF over R times VS. And this is 60 volts right here. But TF over R, that's where we're getting this difference. Okay, so TF is given, and like I said, there's a difference between the two values that are given, the kV and the kT. So there's probably maybe like 5% error introduced through TF, I would guess. Maybe about 5% of the error, or 5% error out of the 30 total. 5 points of that probably come from the TF. And I think that the R is probably where the rest of it comes from. So I would say probably about 20%, or 25%, I guess. 25% comes from R. And that's because R is, if you look, if you look back, it's 1.6 ohms, right? So R is given as 1.6 ohms in the spec sheet. My guess is that actually their values for T max spec is probably better than ours, and I'm guessing that so our omega max spec is pretty close, but their T max spec is different than ours. I bet theirs is better because they probably actually measured that. They probably actually measured the max torque. They probably actually stopped the motor shaft, and they measured how much torque it was putting out at its full voltage. Not totally sure, because you have to be careful with that, right? Because you could burn it out. So over a short period of time, you could do that measurement, though. So I hope that's what they did, because that would be the best way that they would have gone about it. And they also measured this R. But if their R was off by 25%, if they were off, it would have just been like 2 ohms. If it was 2 ohms instead of 1.6, that's 25% of the value of R. So probably the R value is a little bit off. That would be my guess. And maybe they weren't super careful with their measurement. I don't know. There's some uncertainty going on here. Okay, we don't quite know exactly what's going on. There's a little discrepancy. Also, this is for just like the standard motor, right? If we get an actual motor, we should do these measurements ourselves. Because for every motor, R is going to be different. TF is going to be different. So we really should do measurements ourselves and then come up with this model. But in any case, this analysis gives us a lot of information, even if it's, it's a little unsure. We're somewhere in this band, probably, with our speed curve. But when you're designing a lot of systems, 20-30% potential error creeping in isn't a huge deal, because you're going to make it robust enough to handle that. So that's why you'll put feedback on things. You don't assume that your motor model is perfect. You don't assume all the conditions are going to be the same. You use feedback. That's what we'll use. At the end of next semester, we'll be using feedback. We'll be using it probably for motors. We'll be talking about motors and feedback and how to make the speed what you want it, despite the fact that you might not know exactly what the curve is. So, yeah. All right. I'm going to let you guys go. Have a good weekend.